Good day, students. To continue with the discussion on alkene reactions, I want to review first hydration of alkenes because I have something that I want to clarify. For hydration of alkenes, again, we have three ways. We have the acid-catalyzed hydration, we have the oxymercuration, demercuration, and the third one is the hydroboration oxidation nga process. So for acid-catalyzed hydration, this is the mechanism. In the first step, we are forming again the carbocation intermediate. No? So we have our positively charged carbon in here. Okay, and another thing to remember in acid-catalyzed hydration is that this follows the Markov-Nikov addition. That means to say our hydroxyl bonds to the more substituted carbon. Just like in this example, this carbon here is more substituted. That is why we have our OH bonded in that carbon. Okay, again, we have the carbocation intermediate formed in the first step. Now, the thing to remember in acid-catalyzed hydration of alkenes also is that since we are forming carbocation, there is possible rearrangement reaction. Remember the rearrangement, we have the methyl shift, we have the hydride shift. So there is possible rearrangement reaction if a more stable carbocation can be formed. No? Again, so in the first step, we're forming carbocation. Now, after this step, for example, we can have a more stable carbocation. So there could be a rearrangement reaction that will occur. Okay? So you have to remember that. Okay, in this case, in this example, in the first step again, we are forming the carbocation intermediate. Now, our carbocation intermediate here is already a tertiary carbocation. We have 1, 2, 3 carbon atoms bonded to the positively charged carbon. So that is now already the most stable carbocation intermediate. So that is why there are no rearrangement reaction happening in this example. Okay, here the carbocation intermediate form would be a tertiary carbocation. Same here. That is why our OH will immediately bond to these carbons in red circle. Okay? Because it's already tertiary nga carbocation ang ma-form sa intermediate. So most stable already. Okay, for the second way of hydration of alkenes, we have the oxymercuration demercuration process. Now, same with acid-catalyzed hydration, this also follows Markov-Nikov addition. Okay, so that means to say the OH will bond to the more substituted nga carbon. No? So, in between this carbon, for example, this one here is more substituted. So, that is why our OH will bond here. No? Ang nag-differ lang between acid-catalyzed hydration and oxymercuration demercuration process is that, of course, they have different reagents. And the other thing is that the intermediate formed in oxymercuration demercuration process is a mercury cation. So, dili carbocation. It's mercury cation. Now, in this case, there are no possible rearrangement reaction as with the acid-catalyzed reaction. So, after forming the mercury cation, of course, our OH will bond to the more substituted carbon. Again, walay rearrangement reaction like methyl shift or hydride shift nga mahitabo in oxymercuration demercuration process. Okay, so I'll just, now here I have example. Predict the product for each reaction if we have the oxymercuration. These reagents here are for the oxymercuration demercuration process. So what are the products if this follows oxymercuration demercuration, hydration of alkenes, and what would be the product if it's an acid-catalyzed hydration? So let's start with the oxymercuration demercuration process. Again, this follows the Markov-Nikov addition. So our OH will bond to the more substituted nga carbon, no? Sharing the double bond. So in this case, that's the more substituted nga carbon, no? because in the other carbon atom here, we only have 2 hydrogens bonded. Unlike here, we have 1 carbon and 1 hydrogen. So in this case, the OH will bond in that carbon, because again, it follows Markovnikov addition. The hydroxyl will bond to the one of the carbons sharing the double bond, which is more substituted. Okay, in letter B, between the 2 carbon atoms here sharing the double bond, this one here is more substituted. So OH, of course, will bond in that carbon. Now, in letter C, between the 2 carbon atoms here, this one is more substituted. So our OH, of course, will bond in that carbon. So that's for oxymercuration, demercuration process. Now, what if we have the acid catalyzed hydration? Again, as I have mentioned earlier, in the first step, we are forming the carbocation intermediate. So, in this example, in letter A, the carbocation formed here, we have our positively charged carbon here, it's a secondary carbon. Now, and the next carbon here, we have actually a methyl group. No? Now, when we perform methyl shift, a rearrangement reaction, that means to say the methyl will now be connected here or bonded here, and this carbon now will bear the positive charge. Now, what happens when there is methyl shift is that we form the more stable carbocation intermediate. No? From secondary carbocation intermediate, we now form the tertiary carbocation intermediate. Okay? So, that means to say there should be a rearrangement reaction because we are forming the more stable carbocation. Okay. Now, since we have here the positively charged carbon, that is where our OH will be bonded. No? So, in the final product, we have the OH bonded in this carbon. Again, that happens because there is rearrangement reaction to produce the more stable carbocation. So, there is actually a difference, although both acid catalyzed hydration and oxymercuration demercuration process follows Markovnikov addition. There is possible rearrangement reaction for acid catalyzed hydration, no? If a more stable carbocation can be produced. So look at the difference here. In letter A, sa oxymercuration demercuration, automatic lang mag-add ang OH to the more substituted nga carbon, one of the carbons sharing the double bond. Whereas sa acid catalyzed hydration, the OH is bonded here in this carbon, no? Because methyl shift has occurred in the process, no? Okay, how about in letter B? So this is the first step. We are forming this carbocation here. Now, our positively charged carbon there is secondary, no? You have a secondary carbocation. You have 2 carbon atoms bonded to that carbon. Now, in the nearby, carbon on the right, we have actually methyl groups na pwede mag-methyl shift, no? So, for example, we perform a methyl shift. What happens now is that we have the positively charged carbon in that case. So, from secondary carbocation, we now form the tertiary carbocation, which is, of course, more stable. No? So, methyl shift occurs, of course, in letter B because we are forming the more stable carbocation. Now, that is why, in the final product, we have the OH bonded in that carbon. So, instead nga, the OH is bonded in here because we have methyl shift na nag-occur, we now have the hydroxyl bonded in that carbon. Now, so, we have different products. No? In this example, kung acid-catalyzed or oxymercuration demercuration ang i-follow. Sa previous example, again, ako i-mention, wala ta nag-show og methyl shift or hydride shift because the carbocation intermediate nga na-form sa first step is already a tertiary carbocation. So, most stable na siya. So, wala na yung rearrangement ka nag-occur. In letter C, for example, this is acid catalyzed hydration again. So, in the first step, we form the carbocation. Ang atong ma-form ang carbocation will have the positive charge in there, no? Now, that is already a tertiary carbocation. So, of course, the OH will now bond directly to that carbon. So, wala na yung methyl shift nga mag-occur. Okay? So, muna ko ganun i-clarify, ha? for acid catalyzed hydration and oxymercuration demercuration process. Contrary to the two previous ways or hydration of alkenes, hydroboration oxidation is actually the opposite, no? So here, the hydroxyl group is bonded to the less substituted position. So this is anti-Markovnikov. Just like in this example here, the OH is bonded to that carbon because it is a less substituted nga carbon. So that's where the OH is bonded. And also, we have here syn addition. So that means we have the H and the OH bonded on the same face of the pi bond. No? So for example, the double bond is in a cyclic structure. We show the H and OH in the same face by using both naka-wedged or both naka-dashed or broken line. Now, if ever wala siya sa cyclic structure, then we show the syn addition like that, no? Okay, I just like to point it out nga in acid catalyzed hydration and oxymercuration demercuration process, dili siya mag-show if it's syn or anti-addition. So, no need to show like naka-wedged or naka-dashed or broken line. When drawing the products of hydroboration oxidation, it is also essential to consider the number of chiral centers that are created during the process. Diba? I have mentioned nga in hydroboration oxidation, it follows the syn addition. So, same phase, ang H and OH nga mag-attach sa product. But, if there are no chiral centers present sa product nga ma-form, then the stereospecificity of the reaction is actually not relevant. So, no need to show nga naka-wedged or naka-broken line if ang atong product doesn't have any chiral centers. When we say chiral center, we have carbon bonded to 4 different groups. No, dapat 4 different groups. No. In this case, if this is our product, we don't have our chiral center here, no? This carbon is bonded to 2 methyl groups, which is considered as one type of group, no? So, of course, dili na siya ng 4 different groups. If na ay duha ka groups nga, same, no? And in this carbon also, we have 2 hydrogens, so same group lang, no? Now, again, kung walay chiral centers sa product nga ma-form, then the stereospecificity of the reaction is not relevant. No need to show naka-wedged or naka-broken line. Now, when one chiral center is formed, syn addition can occur from either face of the alkene with equal likelihood. So, this is the time that we're going to show naka-wedged or naka-broken line, no? Something like that. So, syn addition man, when we have 2 chiral centers as well, we also have, we have to show, of course, the syn addition nga product. So, pwede nga both naka-broken line or both naka-wedge ang hydrogen and hydroxyl. Okay? Again, kung walay chiral center ang product, no need to show naka-wedge or naka-broken line. It's only when we have 1 or 2 chiral centers ma-formed after the hydration process, no, sa hydroboration oxidation process. And again, the OH is bonded to the less substituted nga carbon. So I think I've shown this in our previous discussion, no, the mechanism, and also this one. Now this is the proof why hydroboration oxidation follows anti-Markovnikov addition, because there is less crowding, no, steric crowding. Okay, so predict the products for each of the following transformations. All of these are examples of hydroboration oxidation. So I have here the answers already. Again, OH should be bonded to the less substituted nga carbon, one of the carbons sharing the double bond, I mean. So in this case, this is the less substituted carbon, so that is where our OH will be bonded. Now, in our product, we have chiral center nga ma-form, no? Asa may chiral center, ana? Pwede diha. Okay, and also here. Okay, recall ha, chiral centers are those chiral carbons. Specifically, in our example, chiral carbons are those with four different groups nga naka-bond, no? So, in this carbon, for example, we have 1, we have this up here, 2, we have the bottom there, 3, and of course, ang wala na show is the hydrogen, which is the fourth group nga naka-bond. Okay? So, that is why in letter A, it is shown nga naka-wedge ang hydroxyl and wala na show sad nga naka-wedge pod supposedly ang hydrogen. Okay, skeletal structure man. So, no need to show the carbon-hydrogen nga bond. Okay, in letter B, do we have chiral center nga ma-form? This one here is chiral center. So, we have to show nga naka-wedge ang OH or naka-broken line ang OH, no? En here stands for enantiomer. So, pwede nga ang atong OH and hydrogen are naka broken line, no? So, mo na siya pasabot sa En. Okay, in letter C, we don't have chiral centers sa ato product. That is why kana sila there are not chiral centers man, no? So, the OH there, as you have seen, wala siya naka-wedge or naka-broken line, no? So, dili siya no need to show the naka-syn addition because we don't have the chiral center sa product. In letter D, this one here is less substituted, so that is where our OH should be bonded, and that there is also a chiral center, so we have to show nga naka-wedge or naka-broken line ang OH. Okay, so this is the summary for the hydration of alkenes. So you have the acid catalyzed. Again here, OH will bond to the more substituted nga carbon. Now take note that this carbon here is already tertiary carbon. So tertiary carbocation ang ma-form. That is why the OH will bond immediately. So walay rearrangement. But if, for example, na ay possible nga more stable carbocation intermediate nga ma-form, no? So mag-occur na siya before mag-add ang OH sa carbocation intermediate. Oxymercuration demercuration process also follows Markovnikov addition, but wala na yung mga rearrangement reaction mag-occur. So, automatic na nga mag-add ang OH sa one of the carbon sharing the double bond, which is the more substituted nga carbon. In hydroboration oxidation, this is non-Markovnikov or anti-Markovnikov addition. So, the OH is bonded to the less substituted nga carbon. And we also have syn addition, nga i-show na to, when we have one or two chiral centers sa product nga ma-form. Okay, so we have here another example. Here we have the three different ways or hydration process of alkenes. No? So, in letter A, we have the, this is the hydroboration oxidation process. So, in letter A, we show nga ang OH is bonded to the less substituted nga carbon. Letter B is the oxymercuration demercuration process. So, we have here the OH bonded to the more substituted nga carbon. Letter C is acid catalyzed hydration. So, let's see if there is rearrangement nga mag-occur. So, letter A, between the two carbon atoms here, this one is less substituted. So, that is where our OH should be bonded. Now, this carbon here is bonded to four different groups, no? So, that is why that is a chiral center, no? So, i-show na to nga naka-wedge or naka-broken line ang OH. Number 2, this one here is the less substituted nga carbon. So, that is where our OH should be bonded. Now, these two carbons here are chiral centers. So, we have to show nga nag-syn addition ang OH and H. Okay? Number 3, this is the less substituted carbon. So, that is where our OH should be bonded. And this carbon here is chiral center. No, so we have to show nga naka-wedge or naka-broken line ang hydroxyl. For number 4, this carbon here is the last substituted carbon. So that is where the OH will be bonded. Now, since we don't have chiral centers for the product, in the product, I mean, no, we don't we need not show the naka-wedge pa or naka-broken line ng hydroxyl, no? Kaya wala may chiral center sa product. Okay, in letter B, this is the oxymercuration-demercuration process. Here, the OH is bonded to the more substituted nga carbon. So, in number 1, this one here is the more substituted carbon. So, that is why din he said mo bond ang OH. Okay. For number 2, this one here is the more substituted carbon. So, that is where our OH will be bonded. Again, sa oxymercuration, demercuration, and acid-catalyzed hydration, wala siya nag-specify if syn or anti-addition. So, dili ta mag-use o katong wedge or broken line. Okay, so, straight lang nga normal line. Okay, number 3, this one here is the more substituted nga carbon. So, that is where our OH should be bonded. No? For number 4, this one here is the more substituted carbon, so that is where our OH will be bonded. Okay, so these are the products when we follow the oxymercuration demercuration process. In letter C, when we follow the acid catalyzed hydration, so again in the first step, we form the carbocation intermediate. So in number 1, diba, in the first step, they should attack the hydronium ion, diba? So after mag-attack sa hydronium ion, one of the carbons here should be positively charged. Now we form the carbocation intermediate. So in this case, this is the more substituted man nga carbon. So that is the one that will bear the positive charge. Okay? So ako lang i-show ha ang carbocation intermediate for number 1. We have here, ako na lang importante ha, supposedly. So that is where our positive charge will go after mag-form sa or mag-attack ang pi electron sa hydronium ion. Now this carbon here, take note, is already tertiary carbocation, no? We have 1, 2, 3 carbon atoms naka-bond. So it's already most stable nga carbocation. That is why anha lang sad mag-attach ang atong OH, no? So there is no rearrangement reaction nga mag-occur. For number 2, again, we form the carbocation intermediate sa first step, and our the carbon that will bear the positive charge is the carbon here, no? And that carbon is already tertiary. We have 1, 2, 3 carbon atoms nga nakabond. So that means to say, anha lang sad mag-attach ang hydroxyl, no? So in this case, same ang product ang atong oxymercuration, demercuration, and acid-catalyzed hydration because the carbocation intermediate nga ma-form sa first step using these reactants, using these alkenes, are already most stable nga carbocation intermediate. Okay? Same sa number 3. Na ang atong carbocation intermediate nga ma-form will have the positive charge here, kaning a carbon. And that is already a tertiary carbocation. No? So, anha lang sad mag-bond immediately ang OH. For number 4, the carbon that will bear the positive charge in forming the carbocation intermediate is this carbon here. Now, that is secondary nga carbocation. Now, when we look sa right, we don't have methyl group. Sa left, wala sa methyl group. So, walay possible nga rearrangement reaction nga mag-occur nga that would produce, for example, a tertiary carbocation. So, in this case, anha lang sad mag-attach ang OH. No? Okay. We cannot perform methyl shift or hydride shift that would produce the most stable nga carbocation, no? From secondary to tertiary. Dili man siya possible ani nga case. So, that is why the OH will also bond in that carbon. Okay, so that's for hydration of alkenes. Here we have how are we going to prepare the following alcohol? Kanina, we are given the alkenes and the different reagents. We are going to predict the product that will form. Here we have the product already. And what we're going to do is we predict unsa nga reactant, alkenes ang starting material, and what could be the reagents nga magamit sad. Okay, so here we have the OH bonded in that carbon. That means to say we could have the double bond here between these carbons here, just like here. Kana siya, 3-methyl-3-hexene. Or we could have the double bond between the two carbons here, just like this one here. Okay, in 4-methyl-2-hexene, we have, for this carbon, these are the two carbons sharing the double bond, and each of these are actually mono-substituted. That means to say each is bonded to one carbon only and one hydrogen. So we cannot compare using Markov-Nikov's rule, no? So that means to say dili ni siya mo ang starting material. Now when we have the 3-methyl-3-hexene, we can now have we have now a difference substitution in the two carbons sharing the double bond, no? Just like here, in this carbon here, we have two carbon atoms bonded, whereas in this carbon, we have one hydrogen and another carbon. So we can compare asa ang more substituted and less substituted carbon. That means to say this should be our starting material, or starting alkene. Okay, in the question, OH is bonded here, no? And this carbon here is the less substituted carbon. That means to say, if this is our starting material, the reagents that we're going to use is the one for hydroboration oxidation, no? Because using this reagent, the OH will bond to the less substituted carbon. So we can form this product when we have the 3-methyl-3-hexene and the hydroboration oxidation nga reagents. Okay, so that is how we predict the reagents and the reactant alkenes. Okay, another example. What alkenes might be used to prepare the following alcohols? So we have to know the different, the starting alkene and the reagents nga gamiton. Okay, for letter A, this is the given nga product. That means to say, we should have the double bond here, no? Sa atong starting alkene. Now, when we have the alkene, the double bond here, in the product, our OH is bonded sa kaninga carbon. And that carbon is actually the less substituted carbon, no? So that means to say, the reagents that we're going to use is the hydroboration oxidation nga reagents. Okay? So you have to familiarize the reagents sa 3-hydration process of alkenes. In letter B, this is the product. So pwede ta mag-double bond between the two carbons here or kana nga carbon. So example lang, when we have the double bonded carbon here, so between the two carbon atoms there, no? So that means to say, asa man ang OH ni bond, naa siya sa kaninga carbon. Na here ba? And that carbon there is the less substituted carbon. So kung mo na atong starting alkene, we should use the hydroboration oxidation nga reagents para maka-form ta sa OH, no? Kaya when we have this alkene, ang OH will bond to this carbon atom here because it's sila substituted, no? When we use the hydroboration oxidation nga reagents. Okay, nakuha. We can also, as I have written kanina, we can also have the double bond between kaninga carbon, and this carbon there. So, kung natay anak nga kanang duha ka carbon, unsa man nga reagents ang gamiton? Based on the product, dinhi ni attach ang atong OH. So, between this carbon and that carbon there, kaninga carbon is more substituted. So, that means to say, atong gamiton nga ang reagents would be sa oxymercuration, demercuration process, and sa acid catalyzed hydration. Kaya himan mo bond ang hydroxyl, no, when we use the acid catalyzed hydration nga reagents and sa oxymercuration to mercuration, no? Okay, because this carbon here is more substituted. Okay? So, for letter C, this is the product given. We can have the double bond dinha na between the two carbon atoms here, or dinhi bakaha, or diha padera, no? Actually, same ra ang kanang duha, no? So, we can have two starting alkenes, no, to produce this certain product. So if we have the carbon double bond here, based on the product, dinhi nag-attach ang OH. So that means to say, ang atong gamitan nga reagents, if that is our alkene, should be the acid catalyzed and the oxymercuration demercuration. Okay, this carbon here is more substituted man, no? So that is why if we have this starting alkene and we use these two reagents, kana nga itong ma-form nga product. Same na sila duha, ha? Okay, so when we use, for example, ang atong double bond is between the two, pwede naman gihapon na siya nga alkene because the OH can still bond here, no? Now, between the two carbon atoms here, this one here is more substituted. So, if this is our starting alkene, we still use the acid catalyzed and the oxymercuration demercuration nga reagents. Okay, so that is how we answer questions like this. So, that's for the hydration of alkenes. Now, we have the catalytic hydrogenation, which is a reduction reaction of alkenes. So here, when we say hydrogenation, we are adding hydrogen to the carbon-carbon double bond. So from alkene, we produce alkane, no? Because we're adding hydrogen. And here we are using metal catalyst. Could be palladium, platinum, or nickel. And this is a heterogeneous reaction which takes place on the surface of a metal catalyst. So, ito siya ang metal catalyst na to. Heterogeneous because we have solid, ang atong metal catalyst, we have gas, the hydrogen, no? So, heterogeneous. And here we also follow the syn stereochemistry. Same sa katong hydroboration oxidation process, no? This also follows syn stereochemistry. That means to say, the hydrogens add to on the same phase sa double bond. So, if the alkene or the carbon-carbon double bond is inside the cyclic structure, to show that the two hydrogens are added in the same phase, we can use either naka-wedge ang duha ka hydrogens or naka-broken line. Now, if the carbon-carbon double bond is not in the cyclic structure na sa alkyl nga chain, then we can show syn addition like this one here, no? So, naka-same parang naka-eclipse. Okay, so this is the mechanism for catalytic hydrogenation. We have our hydrogen here. In the first step, the hydrogen adsorbs to the metal catalyst. So this is our metal catalyst. Then in the second step, we have the alkene adsorbing to the catalyst surface. So sila na sad ang nag-bond with the metal. Okay? And in the third step, we have now the hydrogen transferred from the metal. Diba? Nag-attach ang hydrogens here. So in the third step, we now have the hydrogen transferred. So as you can see here, nag-CH3 na because nag-transfer na ang hydrogen from the metal surface to the alkene, no? And in the last step, we have now the second hydrogen nga ni bond sa carbon here. So we now form the alkane, and remember that the metal catalyst is regenerated at the end. So this is the same thing sa hydroboration, oxidation, katong sa syn addition nga requirement. So kung wala chiral center sa product nga ma-form, syn requirement is not relevant. So we did not show kung naka-wedge pa or naka-broken line ang hydrogens added sa alkenes. Now, if we have one or two chiral centers sa product, then we have to show, of course, nga nag-syn addition ang hydrogens. Okay, predict the products of each of the following reactions. So, in letter A, we determine the number of chiral centers sa mga form. Here we have the 2 chiral centers, so we have to show, in this case, the syn addition. So we have either naka-wedge both ang hydrogens or both naka-broken line. So dapat syn addition. Letter B, for our product, we have 1 chiral center here. So kana lang sa carbon ta mag-show sa naka-wedge ba or broken line, no? Kay kana lang sad ang chiral center. Kani dinhi kadili man chiral center, so no need to show nga naka-wedge or naka-broken line ang hydrogen. So we have here more examples for the catalytic hydrogenation. Okay, so in this example, we don't have chiral center nga na form, so that is why wala ta nag-show kung nabag nag-wedge pa or nag-broken line. So anhing mong add ang atong hydrogens. Okay, you cannot see the hydrogens bonded to carbon kay skeletal man ang structure. In letter B, the hydrogens will be added in these carbons. So again, you cannot see naka-wedge or naka-broken line because we don't have chiral center sa kaninga product. And also, you cannot see the hydrogen naka-add because this is skeletal structure. Same goes sa letter D. No, we don't have chiral center sa product, so we need not show the syn stereochem. For letter C, this one here is chiral center. So we have 4 different groups bonded to this carbon. So we have to show one of the bonds na naka-wedge or naka-broken line. Okay? So that's for catalytic hydrogenation. Now we have dihydroxylation of alkenes. So when you say dihydroxylation, we are adding 2 hydroxyl group. No, di for 2. So we have 2 hydroxyl groups added sa alkene. Okay, so we form this product, for example. Now there are 2 ways sa dihydroxylation, depende sa reagent use. So we can have anti-dihydroxylation or syn dihydroxylation. Okay, when you say anti-dihydroxylation, that means to say the 2 hydroxyl groups are in opposite phases, no? So we form the trans-diol. So naka-opposite phase. Okay, so these are the steps in anti-dihydroxylation. The first step, we have the conversion of alkene into an epoxide. So this is our example alkene. We form this epoxide. And in the second step, by the way, in the first step, we are using the peroxy acid. This stands for peroxy acid. So we can have the peroxyacetic acid or the meta-chloroperoxybenzoic acid. So muna siya ang example nga peroxy acids gamiton for forming epoxide from alkenes. Okay, in the second step, we have now the opening of the epoxide to form the trans-diol. So here we use acid, no? We have the trans-diols. You have seen one of the hydroxyl naka-wedge, the other hydroxyl is naka-broken line, no? So that's how we show the trans-diol. So that means that's for the anti-dihydroxylation. Okay, this is the mechanism for the anti-dihydroxylation. So here we have the formation of epoxide. So na siya ang mechanism for the formation of epoxide. Okay, so one step lang na siya, no? Can you see? I mean, to form this transition state and then to form this epoxide. Okay, we have here carboxylic acid ma-form as well, no? When we form the epoxide. Okay, so we have here the acid catalyzed opening of the epoxide. First step is the proton transfer. So we have here our acid. So we have nag-attack ang lone pair or nag-donate, no, towards this hydrogen here. So ni-bond ang hydrogen, no? Nag-transfer ang proton to this oxygen. Now this oxygen here is neutral, so of course mag-positive charge after mag-proton transfer. In the second step, we have the nucleophilic attack. So we use here water as nucleophile and attacks a protonated epoxide in an SN2 process. So here our oxygen will bond to this carbon here. So it could be bisag asa ana nga carbon. Okay, equivalent pa na siya nga carbon in this case. So in that case, mag-open na nga tong epoxide, no? So we now have here the OH nakabond sa top face in this case, and the water is nakabond sa bottom face. Okay, this is anti-dihydroxylation man. So dapat opposite faces ang two hydroxyl groups. Okay, in the last step, we have proton transfer. So we use another water molecule here which serves as base and deprotonates the oxonium ion. So you remove ang proton here, and we now form the trans diol, no? So we have one hydroxyl sa bottom and one sa top face. So, trans, no? Opposite faces. Okay, predict the products for each of the following reactions. Again, these are the reagents for anti-dihydroxylation. Kanisha is an example of a peroxy acid, and then we have our acid for the acid catalyzed opening sa epoxide. So, in the first step, we determine the number of chiral centers comma form. Okay, so in this case, we have two chiral centers. So, mag-show ta din nga ang usa ka hydroxyl kay naka-broken line, ang usa kay naka-wedge, no? Okay, of course, the two hydroxyl groups will add to the two carbon sharing the double bond. So, tagsaan na sila og hydroxyl. So, one naka-wedge, one naka-broken line. Okay, letter B, so same sa katong hydrogenation, sa hydroboration oxidation, mag-show lang tag naka-wedge or naka-broken line ang atong gi-add if that carbon is chiral center. Okay. So in this example here, kana nga carbon and this carbon here are the two carbon sharing the double bond. So sa ato product, of course, each will have the one hydroxyl nga mo bond. Okay. So in the product, kanilang siya nga carbon sa atong chiral center. So diha lang sa tanag-show nga naka-wedge or naka-broken line. No? The other carbon here with the OH, wala tanag-show og naka-wedge or naka-broken line kay dili man siya chiral center. Okay. Predict the products that are expected when each of the following alkenes is treated with a peroxy acid followed by aqueous acid. Wait lang ha. Okay, so these are more examples for anti-dihydroxylation. Okay, so here we have the two carbons sharing the double bond. So anha mag-attach each one hydroxyl group. Now these carbons are chiral centers. So of course, we're showing one of the hydroxyl kay naka-wedge, the other kay naka-broken line. For letter B, here are the two carbons nga mag-attach ang hydroxyl. Now these two carbons are chiral centers. So we show that one of the hydroxyl kay naka-broken line, the other is naka-wedge. Okay, for letter C, the hydroxyl groups will bond in these carbons. Now these carbons are chiral centers, so we show that one of the hydroxyl naka-wedge, the other is naka-broken line. For letter D, these are the two carbons nga mag-bond ang hydroxyl. Now both of these carbons are not chiral centers, so we do not show kung naka-wedge pa or naka-broken line ang hydroxyl. Sing ana lang ha, if na requirement for syn or anti-addition, mag-show lang ta kung naka-wedge or naka-broken line if we have chiral center sa product. Okay? Okay, for syn dihydroxylation, we say syn, that means to say we form cis diol. So the two hydroxyl groups bonds on the same face of the double bond. Okay, for syn dihydroxylation, so for anti-dihydroxylation, we use the peroxy acid and the aqueous acid. For syn dihydroxylation, we use osmium tetroxide. So in this case, the alkene is treated with osmium tetroxide and cyclic osmate ester is produced. And then, in the second step, the resulting cyclic osmate ester is isolated and treated with sodium sulfite or sodium bisulfite to produce now the diol. So these are the reagents for syn dihydroxylation. We have the osmium tetroxide and the aqueous sodium sulfite or sodium bisulfite. So here we show nga naka same phase ang atong two hydroxyl groups. Okay, because these two here are chiral centers. Pwede sad nga magamit og co-oxidant to regenerate the osmium tetroxide as it is consumed in the reaction. So, in this case, the osmium tetroxide functions as catalyst. So, here are the co-oxidants nga used. We have the N-methylmorpholine N-oxide, which is abbreviated NMO, and the tert-butyl hydroperoxide. So, this is the tert-butyl hydroperoxide. So, pwede sa na siya nga reagents for syn dihydroxylation. Using potassium permanganate, we can also form cis nga diol, no? So this involves treatment of alkenes with cold potassium permanganate under basic conditions. We have the potassium permanganate and sodium hydroxide. This is basic na conditions man. No? So we still form our cis nga diol, or this occurs or follows syn dihydroxylation. Okay, predict the products for each of the following reactions. In each case, make sure to consider the number of chiral centers being formed. Okay, letter A, all of these actually kay what? Syn dihydroxylation, no? So remember, you have to familiarize with the reagents, no? Unsa nga type of reaction, unsa nga reagents gigamit. So for letter A, again, we show kung naka-wedge or naka-broken line ang two hydroxyl groups if they are bonded to chiral centers, chiral carbons. So we have carbons bonded to four different groups. In this case, kaning carbons are chiral centers, so we have to show that the two hydroxyl groups are either naka-wedge or naka-broken line. Kay syn man ta. That means to say same phase na ang two hydroxyl groups. In letter B, this carbon is the only chiral center here. That is why we only show in this carbon na naka-wedge or naka-broken line ang hydroxyl. Letter C, we have the two carbons here which are chiral centers. So we have to show nga naka-wedge ang duha ka hydroxyl or naka-broken line, no? Letter D, both of these, what do you call this? Carbons are not chiral centers, so that is why wala nag-show kung naka-wedge ba or naka-broken line. Is it? That's correct. Okay, for letter E, this is where the two hydroxyl groups mag-bond. No? So, only this carbon here ang chiral. That is why kana lang sad nga carbon nag-show nga naka-wedge ang hydroxyl. So, pwede sad insad nga naka-wedge mag-broken line. Basta mag-show ta nag-wedge or nag-broken line if kana siya nga hydroxyl group is bonded sa chiral carbon. Okay. For letter F, we have these two kana maanhiman mag-bond ang atong hydroxyl. Now, these carbons here are chiral carbons man. So we have to show nga naka-wedge ba ang duha ka hydroxyl or naka-broken line basta kay same phase, no? To show nga same phase, it's either both naka-wedge or both naka-broken line. So this is a comparison between anti and syn dihydroxylation process. Sa anti, again, this produces trans diol, so naka-opposite phase ang two hydroxyl groups nga nag-add. The reagents are the peroxy acid and the aqueous acid. For syn dihydroxylation, we produce cis diol, so the two hydroxyl groups are added on the same phase, no? And the reagents are these. So we have three different reagents for syn dihydroxylation. Okay, starting with an alkene, how would you prepare each of the following compounds? So, since we have the OH bonded in these two carbons, so of course we'll have the alkene in that case, no? So for letter A, man ang atong alkene kay daha man nagbond ang atong duha ka hydroxyl. For letter B, the alkene or the double bond should be here between these two, no? Kay dinha man nagbond ang duha ka hydroxyl group. Okay? For letter C, we have the hydroxyl group here and here. So that means to say we have the double bond between the two carbons here. And we also have another hydroxyl groups in these two carbons. So that means to say we also have a double bond in there. Okay? So these are the starting alkenes of these compounds. Okay, next reaction we have oxidative cleavage of alkenes. So in this case, we form the carbonyl containing compounds. No? So we use powerful oxidizing agents that would cleave our carbon-carbon double bond and produce carbonyl compounds. So this can be done using either ozone in DMS or zinc acetic acid or water. So instead of acetic acid, we have zinc in water. This is ozonolysis reduction reaction. Okay, this can also be done using potassium permanganate in neutral or acidic solution. So using ozone in DMS or zinc in acetic acid, these are the steps. First, we use ozone. So how is ozone formed? This is the equation. So magamit og electric discharge no sa oxygen to produce the ozone. Okay, so the alkene will now react with ozone to form this molozonide. So this is the structure of molozonide. Then mag-rearrange to form the ozonide, and then we form now the carbonyl containing compounds. Okay, so these are the mechanism in producing the molozonide and the ozonide. Okay, if we have we form the carbonyl containing compounds. So if we have a tetra-substituted nga double bond, we form two ketone products. So for example here, if when we say tetra-substituted, that means to say kani nga R here are all alkyl, no? Carbons na sila tanan. So that means to say ining tunga man nato, diba? So here each of these is bonded to oxygen. So this is the first half, and this one here is the second half. So both products are ketone because all of these R groups are alkyl. No? When we have tetra-substituted nga double bond. Now when we have tri-substituted double bond, that means to say tulo lang ka alkyl groups and the last group is hydrogen. So in this case, we form one ketone. So in this kanang part here is the ketone, and the other part here we form the aldehyde nga product. Now, if you have di-substituted nga double bond, so example of di-substituted, kani siya, no? We only have this carbon nga with two alkyl groups. The other carbon kay wala siya alkyl group, no? So, we have two alkyl groups ng di-substituted. So, pwede tang mag-form of, in this case, we form ketone and aldehyde. So, one ketone and one aldehyde. Pwede sad nga, duha ka aldehyde kay. What if ingani ang carbon, ang pagka-di-substituted sa ato, carbon double bond? We have R here and we have one alkyl substituents for each carbon-carbon double bond. So, inig half na to ani, kani will be aldehyde. The other group is also an aldehyde. No? So, depende kung sa kapag di-substitute sa double bond. Okay? So, remember that. Example here, we have tetra-substituted nga double bond, no? So, we have all alkyl groups, mga carbon-carbon, nakabond sa atong duha ka carbon sharing the double bond. So, we form two ketones, no? So, ang buhatan na tungaon lang na siya, okay? So, ilisa na siya, this will be bonded to oxygen, just like here. And this one here, iband sa nimog oxygen. So, mahimo siyang acetone. Okay? Another example, we have di-substituted. In this case, we have each carbon atom which is bonded to one alkyl, no? So in this case, duha ka aldehyde ang ma-form. We have 1, 2. Okay? Because, nga na ganina, because each of the carbon sharing the double bond is bonded to one other carbon atom. So, duha, in this case, duha ka aldehyde ang ma-form. Okay, here we have another example. So, in this example, we have cyclic nga alkene, no? So, inig-add sa ozone in DMS or zinc acetic acid or zinc in water, mag-open na ang cyclic structure. So, what happens then is that, ang sama ni siya nga side. So, ato siya, dinhita mag-start 1, 2. So, this is 1, 2. So, that is where dinhi mo bond ang oxygen. So, we form the carbonyl there. Then, padung na siya dinhi nga side. Okay? So, kana siya is this one here. Okay? So, nag-open ang atong cyclic nga structure. Okay, predict the products of the following reaction. So this is oxidative cleavage using ozone in DMS. So how do we do this? This is according to Klein. Redraw the carbon-carbon double bonds longer than normal. Then, in the second step, erase the center of each carbon-carbon double bond and place 2 oxygen atoms in space. So, tungaon daw na siya, erase ang center. So, this here, gi-erase siya. And then, we place 2 oxygen. So, magbutang tag 1 oxygen here, no? So, oxygen, oxygen, no? So, this is now the product. Not as easy as that. Okay, predict the products that are expected with each of the following alkenes treated with ozone followed by DMS. So, this is still oxidative cleavage. Okay, so sa tayo buhaton, aton siya i-break into 2 and then we add oxygen in that, no? So, for this here, we have kana siya nga product. And then, for the second, mansad na siya. Okay? Here, since na cyclic structure man na siya, sa after oxidative cleavage, ma-open ang ring, ang cyclic structure. Then, we add our oxygen atom sa kanang part and of course, sa bottom side. No? So, mag-add na sa oxygen. Okay? So, this is now the products. Okay, we have 2 structures. For letter B, so kana siya mag-open, kana siya mag-open. Okay, then we add our oxygen sa babaw and oxygen sa ubos. By the way, for these examples, ato tan-awon ha if we have pila ka substituents sa atong carbon-carbon double bond. Here we have pila man ni siya? 1 alkyl, 2, 3 alkyl. So, this is tetra-substituted nga double bond. So, here we have, this will be aldehyde. Then, kana siya will be ketone. No? Okay. Puros man alkyl ang nakabond. In this case, kani siya nga double bond is also tetra-substituted. 1, 2, 3, 4. 4 carbons. Has na po ni sa pikas. 1, 2, 3, 4. So, we expect nga our product are all ketones, no? Kay tetra-substituted man. Okay, letter C, we have this alkene. So, ito na siya i-half. Then, mag-add tag oxygen here for this part. And for the second part, mag-add sa tag oxygen diha. Okay? So, unsa man ni siya? Kana, this is di-substituted nga double bond. So, we expect duha ka aldehyde in this case, no? Kani aldehyde man na siya. And also here. No? So, we have 2 aldehyde nga ma-form. For letter D, this is the alkene. So, after oxidative cleavage, mag-open ang cyclic structure. Then, we add 1 oxygen atom each. No? So, this is what? Diba hydrogen man na siya, no? And also hydrogen. So, we expect nga, natay og duha ka aldehyde nga form, no? 1 and 2. Okay? Identify the structure of the starting alkene in each of the following cases. So, we are given the product after cleavage. Then, atong buhatan is we identify unsa nga alkene ang starting material. Okay, in this case, unsa mo ni siya atong product, diba? So that means to say, kaya naman diha nga itong duha ka carbonyl, kani siya nga carbon atom here, o kana nga carbon are connected. Na? So, therefore, ato siya i-connect, 1, 2, 3, 4, 5, natay 5 nga membered cyclic structure. 1, 2, 3, 4, 5. So, kani siya nga carbon is that 1, no? Na siya methyl naka-attach. And kana nga carbon here is this carbon here. So, na siya ethyl sa nga naka-attach here. Okay, nakuha na siya. So, this is the starting alkene, no, for letter A. Okay, letter B, this is the product. And remember nga, ang atong starting alkene should have 10 carbons. Ang atong product has only 5 carbons lang. That means to say, we have 2 of these di ay nga connected sa starting material or sa starting alkene. No? That means to say, kani siya nga carbon is bonded to another carbon nga ingani sad ang porma, no? So this is our starting material. That is why pag add na to sa reagents for oxidative cleavage, we have diba oxygen makabond diha just like this one. So we have 2 of that, 2 equivalents of this structure. For letter C, ang atong starting material has pila to ka carbons? We have 10 carbons. And then sa atong product, we have 1, 2, 3, 4, 5. That means to say, tagduha day ka na forming nga nga product, no? From the starting material. So that means to say, sa na to pag kanang draw ang alkene, ato na siya isumpay og ingani sad nga structure, no? So di ba ato siya tungaan ha? Tungaan na to. Okay, so pag tungaan na, we have 1 oxygen atom sa babaw, 1 pod sa ubos. So, muna siyang duha ka equivalents ana nga structure ang ma-form. Okay? So, muna siya ang starting nga alkene. Okay, the second way sa oxidative cleavage is using potassium permanganate in aqueous acidic solution. Okay, when we have tetra-substituted na carbon-carbon double bond, we form katong ketone nga products. But in this case, diba, sa katong ozone, kung natay hydrogens nga present sa atong carbon double bond, mag-form tag-aldehyde. But in potassium permanganate, if hydrogens are present, carboxylic acids ang ma-produce instead nga aldehyde. And if we have 2 hydrogens nga present, kung usa lang ka hydrogen ang present, mag-carboxylic acid. But if duha ka hydrogens present sa carbon sharing the double bond, then we form carbon dioxide. Example, we have kana nga carbon sharing the double bond. Kada nga carbon is bonded to 1 hydrogen and 1 alkyl group. No? So, since natay 1 hydrogen nga present diha, the product will have a carboxylic acid nga functional group. And in this carbon here, we have 2 hydrogens present. That means to say, kana siya will become carbon dioxide. Ako ha? Okay. So this is a summary of the oxidative cleavage of alkenes. We have here reaction with ozone followed by zinc and acetic acid. So mag-produce tag mga carbonyl containing either aldehyde or ketone, depende kung pila ka di-substituted ba, tri or tetra-substituted ang atong carbon-carbon double bond. We also have reaction with potassium permanganate in acidic solution. And so when we have tetra-substituted, we form ketone. But if we have hydrogens present, kung usa lang ka hydrogen, we form carboxylic acid. When we have 2 hydrogens nakabond sa carbon sharing the double bond, we form carbon dioxide. Okay, so that's reaction with potassium permanganate in acidic solution. Examples, what products would you expect from the reaction of 1-methyl cyclohexene with the following reagents? So this is the structure of 1-methyl cyclohexene. Letter A is aqueous acidic potassium permanganate. So let's look at the carbon-carbon double bond. Kani siya nga carbon is bonded to 2 carbon atoms. So that means to say mag-ketone ta dihang dapita. Okay? This carbon here is bonded to 1 carbon and 1 hydrogen. So, kani siya nga part, mag-form ta og carboxylic acid. Okay? So, muna siya answer for letter A. Ako siya i-number na lang. The CH3 here is this one. Then, we have this carbon. Kana siya nga carbon. Muna siya ang mag-produce og carbonyl, no? Kay muna siya ang na-double bond. So, siya ang mag-produce sa carbonyl. This CO here is the carbonyl. Then we form CH2, 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 and then for this carbon here, mahimo na siyang carboxylic acid. So we have the CO2H or COOH. Okay? So that's for letter A. For letter B, we have ozone followed by zinc and acetic acid. So, dinhing apart, mag-form ta either ketone or aldehyde. So, kaning part here, for this carbon, it's bonded to carbon and carbon. So, that means to say, ketone na itong ma-form diha nga part, no? So, we have CH3, CH3, then the carbonyl group, kana siya. So, we have CH2, 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 1, 2, 3, 4. And for this carbon here, mahimo na siyang aldehyde, no? Instead of carboxylic acid. Okay? So, those are the different alkene addition reactions. Here we have the different reactions already. No? So, we predict the products for each of the following reactions. Letter A is, unsa man ni siya? Hydroboration. No? Ato na i-answer na lang tayo, no? This is the reagent for hydroboration oxidation. So, we expect mag-add og hydroxyl group sa atong alkene, no? And remember nga, sa hydroboration oxidation, OH is bonded to the last substituted nga carbon. So, that is why din hini-add ang atong hydroxyl. For letter B, kani siya nga reagent is for hydrogenation reaction, no? Hydrogen in platinum nga catalyst. So, we expect nga mag-add og duha ka hydrogen sa atong carbon-carbon double bond. Okay? So, to, sa hydrogenation, we follow the syn addition. So, in this case, again, mag-show lang ta wedge or nakadash if chiral center na siya. Okay? In this case, this carbon is only chiral center, so mula sa na siya naka-wedge. Letter C, what's this? Peroxy. This is for anti-dihydroxylation nga process. So, we expect na mag-add og 1 and 2 hydroxyl groups sa atong carbon-carbon double bond. No? So, we have the 2 carbons here where nakabond ang atong hydroxyl groups. Again, this is anti-dihydroxylation. So, one hydroxyl naka-wedge, the other is naka-broken line. Next, this one here is for syn dihydroxylation reagent. So, mag-add tag hydroxyl diha nga carbon and in this carbon. Now, since the 2 carbon atoms here are chiral centers, so we show nga both hydroxyl groups are either naka-wedge or both naka-broken line. And this one here is the reagent for acid-catalyzed hydration. And remember that in acid-catalyzed hydration, it follows the Markov-Nikov addition. So, OH will bond to the more substituted carbon. So, that is why we have our more substituted nga carbon. For letter F, this is addition of HX. And it follows Markov-Nikov addition. So, the bromine will bond to the more substituted carbon here. Okay? Letter G is anti-dihydroxylation process. These reagents here. So, we show nga both hydroxyl groups nga nag-add sa atong carbon-carbon double bond kay naka opposite phases. No? Okay, both carbons here kay chiral center side. Letter H, this is hydroboration oxidation process. So, OH will bond to the less substituted nga carbon. In this case, this is the less substituted carbon. So, that is where our OH will be bonded. Letter I is a syn hydroxylation nga process. So, we show here that ang OH nga mo attach sa carbons here are on the same phase. No? So, in this case, both naka-wedge. Pwede po nga both naka-broken line. Basta kay syn addition. Okay? So, those are the different examples of addition reactions of alkenes. Here, for the last example, we identify the reagents that we could use to accomplish each of the following transformations. So previous example, we are given the reactant and the reagent. Ang atong buhatan kay we predict the products. In this example, we are given the reactant and the product, and we have to identify unsa nga reagents ang atong gamiton para maka-form ta sa product from that said reactant. So, this is the product. And this is the reactant. So here, we can see that the OH is bonded sa last substituted nga carbon. So that means to say, we use the hydroboration oxidation nga reagent, no, para maka-form ta ani nga product. Letter B, by the way, is elimination reaction. This is formation of alkenes, no, which we haven't discussed yet. So muna siya ang sa next na nga topic. Together with the substitution reaction. So we will discuss elimination and substitution reaction. So later na siyang letter B. Letter C, we add here halide. So this is addition of HX. Okay? So we have here our HBr sa reagent. Letter D, this is from alkene to alkane. So we use the reagents for hydrogenation reaction. For letter E, we are adding this chlorine and hydrogen. So we use the HCl nga reagent. Letter F, we have the OH and the H. So that means to say hydroxylation nga process. Hydration nga process, And this one here is where the OH is attached. So, ang atong gamit nga reagent is the hydroboration oxidation nga reagent. Letter G is also another elimination reaction. So, later na siya i-discuss ang letter G. Letter H, we are adding bromine. So, HX. In this case, we use the HBr. No? Bromine is added to the more substituted nga carbon. Okay? So, that's it for the addition reactions of alkenes.